So today we're going to finish up the last topic before you guys have everything prepared for the test. The last topic that we talked about was operations on functions. I told you about addition, subtraction, multiplication, and division. We defined new functions for those operations because you can't actually operate with functions like that. So we have to create a definition for them. Now there's one other idea of function operation that we need to talk about. This is called 2.8 compositions. Compositions is the idea of having a function. Let's suppose we have a function like a fridge and another function, let's say a microwave. Two different functions. They could be the same, but we're going to assume they're different for now. Two different functions. What happens if I threw one of the functions inside the other? So that is that concept. And this is called composition. So we say the composition f of g, and the way the notation is going to work is going to be denoted as the symbol for that f, whoop, this was like fog, f little o, so a little symbol, g. This is a notation. We're naming this new function this symbol right here. And the input x, we're going to define that function as f of g of x. Remember, when I use the word of, that denotes the input. So when I say f of g, we want to think that, hey, we have f, but we're throwing g inside of f. F of g of x. Now, there's a lot of things we need to talk about this. So the first thing is domain. What is the domain of this new function we just constructed? F of g of x. Well, the domain of that, we know it needs to satisfy. So it must satisfy domain of g and be careful on this. It has to satisfy the domain of g because g has to be defined because we're using g, we're throwing that inside of f. But notice that my input now is not x for f. It's not x. It's g of x. So, and the range of g of x must satisfy f of g of x, or f in this case. So your output for your g has to be included for the inputs of your function f. What does that look like visually? So here's the mapping of that idea. If I create some rem space right here, let's call this set A. Set A is where g is defined. And this set A might have, I don't know, fruits. Let's call this apples. Let's call this oranges. I don't know what else. But that's the idea. Let's just say apples and orange. Now we have a function g. This is g of x. We're going to take an apple or an orange or whatever. We're going to take this function, whatever, is going to take fruit, is going to map fruits all the way into, oops, let me erase this, some space, g of apples, and then g of orange. This space is called the g of x. This is your range. These are your output values. So if I take the input fruits, the output values is over here. This is what a function is. We already know that. Well, now we're going to take this piece. We're going to take everything here, and then we're going to throw that in f. So once we throw it inside f, this becomes, this entire thing, this entire process, we call it f of g. But f oops, I apologize. This f should be over here. Your function f takes all of this stuff, and that's going to be f of g of apples. First, I have to throw an object inside of g, my function g. Then I'm throwing whatever I spit out, whatever that output is, I'm throwing it inside f now. That is my composition function. So it's a double map. That's how you want to think about it. Orange. So let's work with some examples for that so we can get, an algebraic understanding of how this plays out. Example. Let's let f be f of x equals x squared. Let's let g of x equals x minus 3. The domain for both of these functions is going to be all reals, right? X belongs in all reals, x belongs in all reals. We know that for a fact. And you can verify that by graphing it and then checking the domain. But now, if I were to ask you what is f of g of x, so I apologize for making it look like the letter O, but it's not the letter O. It's supposed to be like a little notation, symbol. So this new function f of g of x, well, we're going to define it as f, and then we're going to throw g inside of f. Boom. Now, if I do that, well, my function f, what does the function f do? My function f squares whatever my input is. So, the function f, this is my function f, this is f. It squares anything that's inside my input. Well, what is my input this time? It's not x, it's g of x. This is my input, so I need to throw that in here. This becomes x minus 3. So f of g of x is actually x minus 3 squared. You're going to throw the entire function, this guy, inside f. And now, I hope that you can see why we need we need to satisfy the domain of g. And then we also need to satisfy, or our outputs of g needs to satisfy f. If I get a value that didn't work out for g, the outputs, and I plugged it into f and it breaks, that's a problem. I'll show you that in a bit. But if I calculate this, well, x minus 3 squared, that's the same thing as x minus 3. Don't make this mistake. Don't apply the square on both of them. Minus 3, which is going to give us x squared minus, what is that? I want to say 6x. You can verify if that's true or not. It might not be, but I think it is. X squared minus 6x plus 9. That is your function. So we can say f of g of x is equal to x squared minus 6x plus 9. This idea of composition is throwing a function inside another function. Now, be careful. I want you guys to now calculate g of f of x, or g of f. The x is already implied. Well, this is the same as, hey, I'm going to have my function g, but what I'm going to throw inside of it is f of x. There's a little delay here, unfortunately, but now my function g is over here. What does it do to my input? It takes my input and subtract it by 3. So let's go ahead and write that down. It takes my input and subtract it by 3. Boom. Already have that part. Now, what I'm throwing inside my input is not x. It's f of x. It's f of x. I have to go to where f of x is. Well, this is x squared. I have to throw an x squared here. Boom. So now we have x squared minus 3, and then we calculate g of f of x. That's simply x squared minus 3. Notice that this is not the same as that. The composition of functions, the order does matter. If I throw in this microwave inside this fridge, that is completely different than throwing the fridge inside the microwave. You get different outputs. So be very careful with that. Now, I showed you this. Now we got to talk about the domain. What is the domain of this first one? Well, in this case, f is all real, g is all real, f of g gives you this, and clearly that's all real. So this is all real. So I didn't really make a hard one for this first one. All reals. Likewise, with the second one, you need to satisfy g. It satisfies all reals. Good. So this is definitely part of all real numbers. Now, does the output, your output is going to be x squared. Is that all reals? Yes, in that case. So we can say the domain of this is also all reals. You'll get the feel of this as you get more practice. Now let's try a tricky one. Example. This is another tricky one right here. I like this one a lot. What if instead I wanted to do f of x equals 1 over x and g of x equals 2x minus 7? Well, the domain for the first one is x does not equal 0. Domain for the second one is x is all reals. Alright. So now we got to decide what is our domain for, let's say, f of g of x. Let's do that. F of g of x. Well, f of g of x is simply 1, or let me write all the work so we don't get confused. It's going to be f, and I'm going to throw my g function inside of it. Now my f function does 1 over whatever my input is. This time my input is g of x. So I got to throw this guy inside it. 2x minus 7. So be careful, be careful. You do not need to worry about satisfying this guy. You do not need to worry about satisfying the first part. So we don't really care about the domain of f for now. So we're not going to worry about x is not equal to 0. What we care about by our definition over here, remember it says over here the domain of f of g of x must satisfy the domain of g, which means we need to satisfy the second function, not the first function, the function that is inside our input. That's the function we need to satisfy the domain for. And after that, you need to make sure the range of that function, the range of the second function, satisfy your function f. So over here, we need to satisfy this domain, which is all real numbers. We don't need to satisfy f. We do not need to satisfy this guy. We need to satisfy function g. Now, with the range of g, which is all real numbers, we need to satisfy f with that, which if you see, we have a totally new function. And the domain of this function now is going to be x is not equal to 7/2. If I plug in 7/2 for x, I divide by 0, which is a no-go. So it's the intersection between all real numbers and this guy, which the intersection is clearly the same as this guy. So be careful on that. Now, if I go backwards, however, if I do g of f, your domain changes. So now this is saying I have my function g, and I throw inside f. Well, what is my function g doing? It's doing 2 times my input. 2 times my input minus 7. Now, what's my input? This time my input is f. F is this guy. So it's 1 over x. So if I simplify that, that's going to be 2 over x minus 7 is my new function. This is g of f of x. Well, I need to satisfy function f in this case because f is my second function. So x cannot equal 0. And I have to satisfy the outputs of my function f, the output of this guy, and the output of this guy is all real numbers except for 0. So I have to satisfy that value and then plug it into f. So it just stays as x does not equal 0 in this case as well. Now, what if I instead ask you, hey, what is f of f? What if I throw my function inside itself? Function f inside itself. Well, you can do that. That's just f of x. It might not be the same function either if you do that. our function f is 1 over x. So I'm doing 1 over whatever my input is. But f now, the thing I'm plugging in is 1 over x. So this becomes 1 over x. Which if you calculate that off, that's just 1 divided by x. 1 over 1, or 1 divided by 1 over x. I apologize. So we have 1. Then we're going to divide it, which we turn to multiplication. X over 1, reciprocate it, we get x. Boom. Yep. So in this case, f of x is equal to x. Boom. There's a nice little property with that we'll talk about in a bit. So that's how you can do composition of functions. Now let's do composition of functions and evaluate them. So what function do I want to do this time? I want to do a different one. Let's do the same one. F of x equals x squared plus 1. G of x equals 2x plus 1. All right. And if I were to ask you, what is f of g of 3 this time? All right. So both of these domains are real numbers, so we don't have to really worry too much. Now, when we calculate f of g of 3, well, that means we have to do f, and then we have to find the input is g of 3. Boom. Instead of x, we're going to put 3. Well, this is not too bad to calculate because what it's asking is, hey, I need to calculate g of 3 first. So calculate g of 3 on the side somewhere. If I calculate g of 3, that is 2 times 3 plus 1, which is 6 plus 1, which is equal to 7. Now this problem becomes, hey, my function f, I'm throwing a 7 inside it instead. So this is going to give me 7 squared plus 1. That's my function f, which is exactly 49 plus 1, which is equal to 50. This is f of g of 3. So we got 50. So I'll encourage you guys to try these ones out. Or like a little exercise, try out g of f of 2, g of g of 1, and last one I want to do is f of 2. -1. Calculate these on your spare time. And now, you can also do composition of multiple functions. You can have 3 functions. I'll leave that as an exercise for you guys to determine. But you're following the exact same logic. You're throwing a function inside of a function inside of a function. Or a function inside of a function inside of a function. If you're doing three function compositions. So, that covers compositions. Now we move on to the last topic, 2.8. And this is going to talk about one-to-one and inverses. So before we can go to inverses, we got to talk about one-to-one. What is a function that is one-to-one? Well, let's have this image A. Let's have this image B. And let's let this be apples, oranges, and strawberries. All fruits. All fruits. Now, let's have B be just some number sets. 1, 2, and 3. My function f, we say it's one-to-one if, let's say, apples goes to 1. If I throw apples inside my function, it spits out a 1. If I throw oranges inside my function, it spits out a 1. If I throw in strawberry, it might spit out a 2. The idea a function is one-to-one is if I have 2 inputs that spits out the exact same output. So, a function, definition, function is 1-to-1. Now, if you're in a French class or whatever, they'll call it injective. Injective is actually a better terminology. I would much prefer if students say injective, but so I don't create any confusion with the book, I'll use the word one-to-one, even though I might find it more confusing. A function is one-to-one if no 2 Or I'm sorry, this is not 1 to 1. Not 1 to 1. A function is 1 to 1 if no two elements in A have the same image. That means that if I have an image, let's suppose that f of x1 does not equal f of x2. This can only happen whenever x1 does not equal x2. What it means is that, hey, every single output I have better not have two different inputs. It better not have two different inputs. So we can take an easy example. Let's take f of x equals x squared. If I take f of x equals x squared, well, notice that if I use an actual example, let's say f of x equals 9. This statement means my output is 9. What is my input? What is x? Well, if we remember, whatever squares equal 9, well, that value is just 3. Right? So if I actually calculate this out, just to show you, we can actually calculate this as 9 is equal to x squared. To solve for x, we square root both sides. But remember, when we square root both sides, we have to do a plus or minus. So that means x is equal to plus 3 and x is equal to negative 3. You can do plus or minus 3, either or. But notice that I have two different inputs that give me 9. So automatically, not 1 to 1. Automatically, it is not 1 to 1 because of that fact. And then if we look at this visually, what this image is saying is that, hey, over here, let's take my parabola, my x squared. Notice that for an output, let's say this is 9 over here, y equals 9. I touch the function over here and over here. This is negative 3 and this is positive 3. So it's not 1 to 1 because of that. This is also called the horizontal line test. The vertical line test tells you if you have a function. The horizontal line test tells if you have 1 to 1 function. If your function is 1 to 1. So if it fails the horizontal line test, it is not 1 to 1. Similarly, if it fails the vertical line test, your whatever you have is not a function. Your graph is not a function. Horizontal tells you if it's 1 to 1. Vertical tells you if it's a function or not. So those are two little skills. If I make a horizontal line, it touches my graph at more than one spot. Let's take another one. How do you know if this is a 1 to 1 function or not? Let's say f of x equals 3x minus 4. Is this 1 to 1? Is it 1 to 1? Well, we have to go by the definition. And the definition states that what we're going to be doing, over here our definition, we're going to do something called the contrapositive, which none of you guys might have heard of that. That's in logic. But the idea is that, hey, I'm going to let the outputs equal to each other. I'm going to say, I'm going to have f of x1 equal to f of x2. I'm going to do the opposite of what the definition told me. All right? Now, with this, suppose this is true. Oops, this is x2, I'm sorry. Suppose this is true. That means we have 3 of x1 minus 4 equals 3 of x2 equals, or minus 4, I'm sorry. Minus 4. Now, if this is true, then I better get x1 equals to x2. Let's see if that is true. Well, I can add 4 to both sides. Then I get 3x1 equals 3x2. Then I can divide both sides by 3. Then I get x1 equals x2. Well, they are equal to each other, so this is 1 to 1. This is the idea. So instead of showing you this definition, I'm instead going to do the negation of it. I'm going to say, hey, assume they're equal, then I better have x1 equals x2. I better, if my outputs are equal, then my images better be, pre-images better be the exact same, my inputs. So I'm doing the reverse of that statement. That's called the contrapositive. So we can test if a function is one-to-one by doing this little rule. Now let's use that same idea with f of x or equals x squared. If I did it with this instead, let's see what happens. So I assume f of x1 is equal to f of x2. Well, that's the same thing as saying x1 squared equals x2 squared. But the problem is when I solve for the variables by square rooting, I have to do a plus or minus. So I get plus or minus x1 equals plus or minus x2. And they are not the same. Because what this is saying is that, hey, if my x1 is positive, my x2 could be negative. If my x1 was positive, or if it was negative, my x2 could be negative or positive, whatever. So it could be alternating. So that means we don't have a one-to-one function. So why do I even do that? So the good side, though, even if it's not one-to-one, f of x equals x squared, even though this function is not one-to-one because it fails the horizontal line test and by definition it doesn't work, what we can do instead is restrict its domain, like how we do it piecewise. So if I restrict my domain to x only being positive value, and I erase this portion of my quadratic, notice that this does pass the horizontal line test. So we can say this function is one-to-one if I restrict the domain. If I need this part right here. If I do not have that part, then it is not one-to-one. So why do we even talk about one-to-one in the first place? Well, one-to-one and horizontal line tests or whatever, they bring a very important role into functions, and that's called inverses. The final topic, inverses. What are inverses of functions? So inverses of function, we say f has an inverse, and this is the notation, this guy right here. Now be careful, that is not raised to the negative first power. Not raised to negative first power. That's why it's very confusing. This is a symbol. It's a symbol. I think it's an outdated symbol, but you know, at the end of the day, is what we've been using for so long that we haven't changed it yet. But this symbol represents inverses. You are not raising your function to the negative first power, so do not make that mistake. This is the inverse function, and in particular, we say f has an inverse if f is one-to-one on domain A and range B. Then, so if f has a domain A and range B and it's one-to-one, so it has to be a one-to-one to have an inverse, then f inverse has domain B and range A. So it's flipped. It has the domain of the range of f, and it has the range, or it has its range is the domain of f. So it's swapped. So you gotta be careful. So the idea is that if I have a one-to-one function, let's say f of x equals y. Let's suppose this is one-to-one. You know, if I plug in an x value, I get a y value out. Your inverse function, this means your inverse function takes the y value and it will spit out the x value. It takes the y value and it will spit out the x value. It's reverse. Its y value is your original x value. Its x value is your original y value. So the idea is very simple. Boom. Boom. Let's call this A. Let's call this B. Domain A, domain B. All right, your function f does this 1, 2, 3, 4. And this does, let's say 10, 20, 30, 40. I'm going to give you a one-to-one function. This is a very easy one-to-one function for me to create. Boom. Notice that none of the outputs have different input, or there are no two inputs that have the same outputs. So this direction, we call it f. Now, if I go in the backwards direction, I call this f inverse. F goes in the forward direction, f inverse goes in the backwards direction. So we can do some exercises with that then. So what if instead I ask you, hey, can you calculate the inverse function if I have, let's suppose, I gave you f of 1 equals 5, f of 2 equals 3, f of 4, or I'm doing f of 3. F of 3 gives you negative 8. Suppose f was 1 to 1 right here. Could you calculate these right here? What is f inverse of 5? What is f inverse of 3? What is f inverse of negative 8? Each of these three. Well, remember, it spits out the x, it takes the x value. If your function takes the x value and spits out a y value, your inverse takes the y value and spits out the x value. So right here, my x value is 1 and it spits out a y value 5. So if my x value is 5, it's going to spit out a 1. Likewise over here, the y value is 3, but the x value corresponding is 2. That means if I throw in a 3, it should spit out a 2. And then the last one, I spit out a negative 8. That means it's going to reverse that. So if I throw in a negative 8, it should spit out whatever this is. Boom. This is what your inverse function does. It swaps the x and the y values. So so this is good if I give you the inputs and outputs. What if I didn't give you that though? What if instead I gave you something like 3x, so let's say y is equal, let me use f of x. So what if instead I gave you f of x equals 2x plus 4? And I ask you, what is f inverse of x? If I ask you for the equation of the inverse function. Remember, you're not raising to the negative first power, so don't make that mistake. Well, what you're going to be doing here is the idea of swapping the x and the y's, because that's what our inverse function does. It swaps x and the y's. So remember, this is also a y value. We can call this the output or y. So let's just replace that. Well, if I replace that now I can swap the x and the y values. Let's put x over here and let's put y over here. Now this is my inverse function, but I didn't solve it out. So now I need to solve for y. Solve for y, swap x and y. This is how you find your inverse function. You swap the x and the y, and then you solve for y. Well, to solve for y, I gotta get rid of this minus or this plus 4. So I gotta subtract 4 to both sides. So I get x minus 4 equals 2y. And I divide both sides by 2. So I get y is equal to x halves minus 4 over 2. Which is the exact same thing as saying y is equal to 1/2 x minus 2. This is f inverse of x. So we're able to find the inverse function. Now, let's do another one just to be sure. What if instead I had an inverse function like, let's say f of x, let's do g this time. G of x equals, let's do square root of x plus 2. Find g inverse of x. Well, again, I'm going to turn this into a y equals square root x plus 2. Now I need to swap the x and the y. Swap x and y. So if I swap the x and the y's, I get x is equal to square root y plus 2. To solve for y, to get it by itself, I have to get rid of this guy right here, which that means I got to square both sides. So apply the square. So I get x squared is equal to y plus 2. Subtract 2 to both sides. I get x squared minus 2 equals y. Or we can say it's going to be f of negative inverse of x is equal to x squared minus 2. That's our inverse function. Now, there's a little subtlety that I did not cover because, remember, this is x squared. It's not supposed to be 1-to-1, so we're not supposed to have an inverse. We're not supposed to have an inverse. And the reason why we're not supposed to have an inverse, well, this function, if I drew it out, is supposed to be this, right? Something like that. Something like that. Maybe I went left 2, so let me be more precise. I went left 2. If I did transformation, left 2. Boom. That's my function originally. This is f. Or g of x, I'm sorry. This is supposed to be g. My g of function, g of x, is this guy. Well, once I found the inverse, it says the inverse is x squared minus 2. It said it's this guy right here. Let's see. What's the problem though? So the biggest issue with this is that when we're actually finding the inverse, believe it or not, it's supposed to be reflected about this axis. It's supposed to be odd in that idea. So that means this part of my function shouldn't even belong there for my inverse. So we have to include this last part. This would be my inverse, but I also have to add in a little note that x has to be strictly positive, or let me write this down. Has to be strictly positive. So I'll say x plus 2 is strictly positive. Boom. And why do I say x plus 2 is strictly positive? Because over here, this is not square root of x. This is square root of, well, originally, it's square root x plus 2. So I have to say that entire expression has to be positive because I don't want to square root a negative number. So boom, you have to put that restriction on for that inverse function. So I can find my inverse only if it's 1-to-1. If it's not 1-to-1, then I will have to restrict the domain to where it is 1-to-1. So I encourage you guys to try more exercises. So try this one out and then we'll call it a day, or not yet. So try doing f of x equals 3 of x plus 2. And then the last thing I want, this is this really neat property that we've seen all the way up here with compositions. If you notice, with composition 1 over x, we had something nice happen, but I'll talk to you about it right now. So if f is, or if, let f be a function. Let f be a function. G is an inverse of f. If G is the inverse of f, if f of g of x is equal to f of g of x, which is equal to x. If you do the composition of the two functions and you get f, and then if you do the reverse composition and g of f of x is equal to g of f of x equals x. If I do the composition in the forward direction and in the backwards direction, I get x. That's how I know it's inverse. Then f inverse is equal to exactly g. So if I take a function and I take the inverse function and I did a composition of it, if I threw it inside each other, I should spit out an x. Why is that true? Well, it's the idea where if I have my machine, if I have my mapping or whatever, let's suppose this is x. This is x. If I throw it over here, which is f, but then this is f of x, right? Then if I go into my next machine, well, if this is supposed to be my next machine, if this was the inverse though, that means I'm going straight. Instead of going forward, I'm going backwards. This is supposed to be f inverse. If I throw f into it, I get f of x. But if I go backwards, then I get x back. So instead of having a three-way map for composition, this is supposed to be F, or this is supposed to be, I'm sorry. X is supposed to be here. F is the mapping right here. This is F of X. And then the last part is supposed to be G of F of X. Instead of this third mapping, it's just going to go, instead of this third mapping, I'm actually going to go backwards to the first one. And that's why we're going to get X back out if it's the inverse function. And I'll leave it at that. So now that you guys have all the tools to, or all the topics for test number 2, if you guys have any questions on Monday, be sure to join office hours, or I'll schedule a time probably around 5 p.m. to see if anybody wants to join. And if anybody wants to join, I can answer any questions before the test. Make sure you try that review out that I gave. It's in your, I believe it's on your weekly assignments. If you look in weekly assignments chapter 2, it should be listed there. So go ahead and give those a shot. I will catch you guys later. Take care.